So let's first start off with the composition of clay. The minerals of clay can be found in 60% of the Earth's crust. It usually contains alkali and alkaline earth metals. The most abundant are oxygen, silicon, and aluminum, followed by iron, calcium, sodium, potassium, and magnesium. The most important mineral of clays consists of kaolinite. Kaolinite consists of a 1-to-1 ratio of aluminum oxides and silicon. The crystal structure shows plate-like particles, which are stacked in layers linked by hydrogen bonds. It is through the structure, properties, and transformations of kaolinite that we can understand the physical changes involved in making of a pot. So next up, we have the composition of glaze. Liquid glaze is composed of silicon dioxide, aluminum oxide, and fluxes, which are typically consisted of alkali or alkaline earth metals. The purpose of the aluminum oxide is enhance the viscosity of the glaze by cross-linking the silica networks. The purpose of fluxes is to lower the melting point of the mixture to the temperature of the firing. So now we have the firing process of clay. Before firing the vessel, it's essential to make sure that the vessel has air dried thoroughly. Placing the vessel in the kiln with too much moisture will cause the vessel to explode. At approximately 212 degrees Fahrenheit, the steam of the excess moisture creates air pockets to form, gradually building more pressure as the heat increases. As the pressure is over-exceeding the small volume pocket, it causes the pocket to burst with the overabundance of molecules. It's important to note that the changes are irreversible, meaning once the vessel has reached 500 degrees Celsius, the vessel is solid and non-pliable, so therefore it can no longer be worked with like it once was. This reaction represents the weaker hydrogen bonds being replaced with stronger oxygen bonds. At the same time, the regular sheet-like crystal structure of kaolinite is being lost, and amorphous metakaolinite is being formed. Once the vessel reaches 1000 degrees Celsius, the vessel will begin to decrease slightly in size. When it reaches this temperature, the hardened clay, known as biscuitware, is quite porous and strong. The phase diagram below demonstrates a mixture of composition indicated by the red line. When it reaches the temperature TE, it begins to melt. As the temperature rises, the proportion of the solid diminishes, and the proportion of liquid increases until the last of the solid melts. The graph represents the shrinkage curve of a ceramic while being fired. Once the temperature reaches 1200 degrees Celsius, the curve dips down drastically. Representing the hotter the ceramic becomes, the more the size is decreasing due to the solidification. When it is heated to high enough temperatures, the water molecules are driven off. The buildup of heat must gradually increase, otherwise instant high heat can cause the ceramic piece to explode. The silica oxide, known as quartz, which is a crystalline structure. When the ceramic is heated, inversion of the crystalline structure occurs. The size increases by 2%, and while it cools, it decreases by 2%. So finally, we have firing process of glaze. Fluxes provide color to the ceramics. You can find glazes looking like a light red and turning out to be a dark blue after being fired. Glazes also have different properties, such as textures. Some glazes have little rocks that burst with color when fired. Another property is opacity. Some glazes can result with being clear or opaque. Silica is the structural material for the glaze, and if you heat it high enough, it can turn into glass. Its melting temperature is too high for ceramic kilns, so silica is combined with fluxes, substances that prevent oxidation, to lower the melting point. Aluminum oxide is used as a stiffening agent, allowing the glaze to adhere to the surface of a bowl or vase without runoff. Glazes get their colors from a wide variety of mineral oxides. Electric kilns always fire in oxidation, meaning there's oxygen present in a completely controlled environment, which yields the consistent results with glazes. This control is important for a potter who wants to replicate their work.